this was a magnitude 5 earthquake. It was not at 100 kilometers, it was at 220 kilometers, but we corrected for that using this nonogram. Okay, does that make sense? So, how much smaller would the amplitude of the ground motion be if the earthquake was 1 magnitude unit smaller? So just look at this plot and estimate what you think the amplitude would be if this was a magnitude 4 earthquake rather than a magnitude 5 earthquake. Okay, so everybody done it? Obviously the point purpose of doing this is so you understand how the diagram works. Okay? Somebody want to tell me what they're seeing? Yeah? Right, somewhere between 2 and 3. In fact, it's exactly 2.3. Okay? All right, and so that's not a coincidence. This was 23 millimeters. This is 2.3 millimeters. Right? This is 1 magnitude unit lower. It is a factor of 10 smaller. That's why this is a magnitude scale, a log to the base 10 scale. That's why this factor of 10 comes from. So if we're seeing a 23 millimeters on the Wood-Anderson instrument, 23 millimeters for a magnitude 5, if the earthquake was 1 magnitude unit smaller, you would get exactly 2.3 millimeters. And if it was another magnitude unit smaller, a magnitude 3, you would get 0.23 millimeters. Okay? So that's just, that's exact. That's the definition of the scale. That's why it's exact. Okay, so now how much closer would you need to be to get an amplitude of 23 millimeters for a magnitude 4 earthquake? Okay? So we're now going to keep this fixed and do a magnitude 4 earthquake, and how much closer do you have to be? So this one is at 200, right? So this one for the magnitude 5 is at 210, 220 kilometers. Anybody come up with an estimate? Somebody from the back, maybe? Yeah. About 60 kilometers. Right, so when I draw a line, you get to 50 kilometers. So if you wanted to see the same amount of ground motion, but for a smaller earthquake, magnitude 4 earthquake, you would have to go to a seismometer or a Wood-Anderson instrument that was 50 kilometers away from the event rather than 210 kilometers. So there's no simple relation here. This is then, the simple relation is the magnitude and the amplitude because that's how it's defined. But obviously you have to move closer to see stronger ground shaking. Okay, does everybody get it? So you're going to be doing this as part of assignment 3. I want to make sure everybody has got it. Okay? But so this again, the other thing to emphasize here is that the magnitude scale is this empirically defined scale. Okay? And we don't use Richter magnitude anymore because we don't have Wood-Anderson instruments anymore. However, the scales that we do use, they're still largely empirically defined. Okay, so what we use today, rather than Richter magnitude, we use what we call local magnitude. Okay? And so the local magnitude, what you do is same sort of approach. You take the log of the amplitude that's been observed, and then you make a correction for the distance. Exactly the same thing that we were doing with the Richter magnitude. And so, so the other thing to recognize is that for every single seismogram, you estimate the magnitude. You only need one seismogram to estimate the magnitude of the earthquake. All right? So the way that we determine the event magnitude is we make an empirical observation with every seismogram. So every seismogram gives us one estimate of magnitude, and then we average all of those magnitudes to get what we define as the magnitude of the earthquake. So it's an empirical process, it's an empirical observation. Okay? So there are other magnitude scales that we use. So the local magnitude is kind of the modern-day equivalent of the Richter magnitude. The Richter magnitude, he was in Southern California, and so it was defined to detect or to estimate the size and compare the size of different earthquakes in Southern California. So it's kind of on a regional scale. All right? So the local magnitude is still used on a regional scale. Northern California has its local magnitude. Southern California has its local magnitude. But when we want to kind of go up to a global scale and have a consistent measure of magnitude, body wave magnitude is one way that we do that. And the body wave magnitude is estimated using the P-wave arrival. So the P-wave body wave measured at any station anywhere in the globe can be used to estimate the body wave magnitude of an earthquake. And again, there's the amplitude. It all comes back to the amplitude. In the case of the body wave magnitude, we take the amplitude, the log of the amplitude. We actually use the period, which is the duration of one oscillation, and then there's a distance correction. Okay? You don't need to worry about these details. They all use the amplitude, and the difference is that the body wave magnitude is using the amplitude of the P-wave at teleseismic distances. So at the back of your textbook is an example of estimating magnitude in various ways for an earthquake recorded at Orville. This is Appendix G of your textbook, so I'm just going to use that as an example. So they show there the P-wave was measured as being 1.4 times 10 to the minus 6 meters, so tiny, tiny motion, of course, and this is the period. And so you just stick that into the equation, and you get that this earthquake recorded at Orville was a magnitude 5.3. Okay? So the second magnitude estimate is the surface wave magnitude estimate. Not surprisingly, we use the amplitude of the surface wave rather than the amplitude of the P-wave. Okay? But again, for the surface wave magnitude, we use the amplitude, and then there's a distance correction. Okay? These are still empirically defined relationships. That's why they're always a little different. So you take the same, the Alaskan earthquake, sorry, did I say that on the last slide? Oh, yes, sorry, I missed that. So it's Alaskan earthquake recorded at Orville. Now we already did the P-wave. If we now look at the ray wave, which is the surface wave, the amplitude is 4.3 times 10 to the minus 6. So you can see it's actually bigger than the P-wave, just as you would expect, as shown in this little cartoon. So it's 4.3 rather than 1.4, both are times 10 to the minus 6. Sorry, that should be an exponent. Stick that into the equation, and we get a magnitude 5.0. So surface wave magnitude 5.0, body wave magnitude 5.3. They're different. Does that surprise you? Some people are nodding their heads. So magnitude, while it's true that the idea of magnitude is that there's one magnitude estimate for an earthquake, when we use these different empirical relationships, we get slightly different answers. Okay? So it's not surprising that we get 5.0 versus 5.3, slightly different answers for these two cases. All right? So it matters when people report the magnitude, which magnitude scale it is that they're using, so that we can, if we want to compare one earthquake to another earthquake, then we need to understand which magnitude scale is being used, so that we can compare like with like when we're comparing different earthquakes. Is that a question? Yeah. So the question was, is one magnitude more often used than another? The answer to that is yes, and it's neither of these. I'm going to come to the preferred. So we have a preferred magnitude scale that we, the seismology community, uses now, and that's coming in a few months. Yeah. These have been used for a long time. The one that we prefer to use now is a more recent addition. Okay, so another important thing is that you can actually use the difference between surface wave magnitude and body wave magnitude to characterize differences between earthquakes, and more specifically, between earthquakes and explosions. Right? So when you have an explosion, we talked about this last week, the energy that's being radiated out for an explosion. When you have an explosion, it's all this compressive energy that then is being radiated out. Whereas when you have an earthquake, there's this sort of strike-slip, there's the side-to-side motion, shear wave energy. So explosions generate lots of P-wave energy, but they don't generate very much S-wave energy, or surface wave energy, while earthquakes do generate more surface wave energy. So if you actually compare the body wave magnitude and surface wave magnitude, you can use that to discriminate between explosions and earthquakes. And so here's an example where we're just taking a whole bunch of events, and we're plotting the body wave magnitude versus the surface wave magnitude. The earthquakes are all along this line, and the explosions are all offset, because they all have larger body wave magnitudes than their surface wave magnitudes. So this is useful for what? Why might we want to know if it's an explosion versus an earthquake? Yeah? An explosion might mean something's wrong, something needs to be fixed. That's true. Yeah. So you can react to it appropriately. That's true, but what are these explosions, do you think? Again? War? W-A-R? Okay, war, right. Bombs. Yes, nuclear bombs. So the key issue here is that this is one of the main discriminants that has been used to distinguish between nuclear tests and earthquakes. So in the era of trying to control nuclear weapons, being able to see whether people were testing nuclear weapons or not and understanding the tests that they were doing, being able to distinguish big explosions from earthquakes was a major undertaking, and this kind of discriminant was one of the main ways that was used. What's another way of determining an earthquake versus an explosion? What's a characteristic of an explosion that's not true for earthquakes? Say again? Okay, so an explosion is more impulsive, while an earthquake is more continuous. That's true, although earthquakes can be fairly impulsive as well. Yeah. Sonic waves, acoustic waves in the atmosphere, they do make a difference. Yeah, you're not going to get sort of what I was looking for is depth. If you're doing a nuclear test, you basically have to do it at the surface of the Earth. Right? You can't drill a hole more than a few kilometers deep. That's as good as being at the surface of the Earth. Whereas, of course, earthquakes can happen down to hundreds of kilometers. So depth is the other key discriminant. All right, so now we have a magnitude scale. We can talk about the Gutenberg-Richter relation, which is how many earthquakes of different magnitudes we have. So it's not going to be a surprise. We have fewer large magnitude earthquakes than small magnitude earthquakes. We have many, many more small magnitude earthquakes. The Gutenberg-Richter relation tells us how many small earthquakes we have for every large magnitude earthquake. Okay? And so this is the Gutenberg-Richter relation that shows that, again, it's a logarithmic scale. This is log of n is the number of earthquakes. Okay? And this is then the magnitude along the horizontal axis here. The numbers are actually written out here. So greater than a magnitude 8, somewhere between 0 and 1 per year. A magnitude 7, 18 per year. This is an average, I think. Magnitude 6, 120. Magnitude 5, 800. Magnitude 4, 6,000. What this comes down to is that because this is a logarithmic scale, and this gradient of this line is about 1, essentially there are 10 times as many magnitude 4 earthquakes as there are magnitude 5. And there are 10 times as many magnitude 5 earthquakes as there are magnitude 6. All right, so again, back to the logarithmic scale. In round numbers, there are 10 times as many magnitude 4 as there are magnitude 5. Okay? So this kind of tries to put these various things together. The width at the bottom here is the number of earthquakes, and then the height here is the magnitude. And so we have many more. So magnitude 2, there's about 1 million per year. Magnitude 3, 100,000, 12,000, 2,000, right? Less than 1 once you get up to a magnitude 9. And what is shown on this side is some of these big earthquakes, the Chile earthquake, the Alaska earthquake. This figure was put together before the Sumatra earthquake, so that's not shown, and neither is the Japan earthquake that we were talking about. And then on the other side, down here, are some of the energy equivalents for various things. This is the Krakatoa eruption, so a big volcanic eruption. This is the world's largest nuclear test, okay? Basically the equivalent of a magnitude 8 earthquake. The Mount St. Helens eruption, so the largest nuclear test, released more energy than the Mount St. Helens eruption. This is the Hiroshima atomic bomb. An average tornado is around about the equivalent of a magnitude 4.5 earthquake, etc., lightning bolts, etc., okay? And then on the right-hand side here is an estimate of the approximate energy equivalent, okay, measured in equivalent kilograms of explosives. So this comes from the nuclear testing era, which is how you would measure the size of a nuclear test. And so you can see what the scale looks like. You can see that this scale obviously is also increasing exponentially, and that again is because this is a magnitude scale. All right, so this is the link between magnitude and energy. The two are related to one another. This is a magnitude scale, energy is not, and so this increases exponentially as you increase the magnitude of an event. Okay? So how do we estimate the energy of an earthquake? It's actually very difficult. If you wanted to estimate the total energy of the earthquake, you can imagine the earthquake occurring. You would need to have sensors all around the earthquake to capture how much energy is being radiated out in all directions, because more energy might go in one direction than in another direction. So it's a very difficult thing to do. However, we can estimate the energy released in an earthquake, and this is one very simple equation that estimates the energy based on the surface wave magnitude. So a very simple equation, plug in the surface wave magnitude, and you get the energy. And if you play around with this, what you will realize is that a magnitude 5 earthquake releases about 30 times as much energy as a magnitude 4. Okay, so don't get these things confused. Keep them straight in your head. There are 10 times as many magnitude 4 earthquakes as there are magnitude 5, but one magnitude 5 releases 30 times as much energy as one magnitude 4. Okay? So that means that the 1 magnitude 5 earthquake releases 3 times as much energy as the 10 magnitude 4 earthquakes. So the big earthquakes release most of the energy. So when we talk about the total energy release due to earthquakes around the globe in a given year, it is the one largest magnitude earthquake that releases most of the energy. Okay? So this comes back, people have asked this question a couple of times in several ways. Could we, with the fluids, when we're talking about fluids, could you pump fluids into a fault and create many small magnitude earthquakes so that you don't have a large magnitude earthquake? The problem is that it's the one biggest earthquake that releases most energy. Okay? That's the challenge. That's why that approach does not work. Okay? So we can plug in our, so we go back to our Alaska earthquake and we can estimate the energy. So you just take the magnitude 5 surface wave magnitude, you plug it into this equation, and you get 2.0 times 10 to the 19 ergs. How many of you have heard of ergs? 1. Ergs is a unit of energy that nobody uses anymore. The reason I'm using this is because this is the example from your textbook. We would use joules, of course, today, but I'm leaving it like this because this is what's used in the textbook. And so to make some comparisons, the US annual energy consumption is 10 to the 26 ergs, so obviously bigger than a magnitude 5 earthquake. Annual heat flow out of the Earth is 10 to the 28 ergs, so there's actually more heat coming out of the Earth than we use just in the US. Of course, most of our, well, actually, I won't go down there. The annual seismic energy release is somewhere between 10 to the 25 and 10 to the 26 ergs, okay? So the total annual seismic energy release is sort of similar to the total energy consumption in the US. If we could somehow harness all of the seismic energy released around the globe, we could power the US. Okay, of course, we can't do that, but just in terms of give you a sense of the amount of energy that we're talking about. All right? Okay, so finally, seismic moment. And so somebody asked me which is the preferred magnitude scale. So the preferred magnitude scale by seismologists is what's called the moment magnitude. And the moment magnitude is directly related, as you'll see in a minute, to the seismic moment. And the seismic moment is a measure of the physical, it's a more physical measure of the earthquake. All right? And so the seismic moment, you can think of it, this is a force couple. So if you think of having a beam of some kind and you have a force on the two ends of the beam, the force couple, the total force couple, the moment of the force couple, is the length that's separating these two forces multiplied by the force. So you can kind of see that this is similar to what happens in an earthquake. In an earthquake, you've got these forces pushing on the tectonic plates, you have a fault in the middle, and you have offset. And so that's sort of just to try and give you some kind of conceptual reasoning why we like this kind of approach. And so the seismic moment is proportional to the size of the fault times the slip on the fault. So seismic moment is defined, this is a constant, I'll come back to this, times the area of the fault that slipped, times the average displacement on the fault. That's the definition of seismic moment. This mu here is the shear modulus. So that's a scaling constant. So seismic moment is the shear modulus times the area of the fault that slipped, times the average amount of slip on the fault. That's the definition of seismic moment. And so then the moment magnitude is related to the seismic moment. Seismic moment is m0 right here. And then moment magnitude is simply related to the seismic moment by this equation. And again, this is an empirical relationship defined by Hiro Kanamori a few decades ago. And so this is our preferred magnitude scale. Whenever any seismologist talks about the magnitude of a significant earthquake, they will be using the moment magnitude. Whether they say it's moment magnitude or not, they're going to be using the moment magnitude. Because if they don't, the rest of the seismology community will chastise them. So moment magnitude is our favored measure. In the case of the Alaskan earthquake measured at Orville, the total seismic moment was 4 times 10 to the 23. Plug that into here, you get a moment magnitude of 4.9. So seismologists would report this event as being a magnitude 4.9, as opposed to a body wave magnitude of 5.3 or a surface wave magnitude of 5.0. Okay, one last simple scaling relation, so you have a sense, is the length of the fault. It sort of scales with the magnitude, and here's another empirical relationship relating the length of the fault to the surface wave magnitude. So if we plug in the surface wave magnitude and you do the calculation, you find out that for the Alaska earthquake, the length of the fault was about 3 kilometers. Okay? So I just want to show you these simple relations. I want you to understand the difference between the different magnitude scales, and I want you to have some simple relations that you can use to estimate how much energy is released in an earthquake, what the total length of the fault that erupted in an earthquake might be. That's the idea here. Okay? So finally, just to compare some of the earthquakes we talked about the Pakistan earthquake, 2005. So it had a body wave magnitude of 6.7. It had a surface wave magnitude of 7.7. It had a seismic moment of 2.9 times 10 to the 27. And it had a moment magnitude of 7.6. And if you estimate the energy, this is what you get. If you estimate the length, it's 190. Now, these numbers are very similar. Surface wave magnitude, moment magnitude, very similar. This number is not. Okay? And that's because a body wave magnitude is only a reasonable estimate of magnitude up to about a magnitude 6 earthquake. Once you get to earthquakes bigger than magnitude 6, the body waves don't really increase in amplitude. And so body wave magnitude isn't a good way of measuring magnitude for earthquakes bigger than 6, and that's why you get this lower number. Here's the Loma Prieta earthquake. The body wave magnitude for the Loma Prieta earthquake was 6.5. Surface wave magnitude was 7.1. The moment magnitude was 6.9. So that's why you always hear me call it a magnitude 6.9 earthquake. I hope I've always called it a magnitude 6.9 earthquake. The total length of the fault that ruptured was about 30 kilometers, right? So this is quite a bit smaller, obviously, than the Pakistan earthquake. And then finally, the Sumatra earthquake that we started with today, its surface wave magnitude was 8.9. Its moment magnitude is 9.3. And so the total length of the fault is about 10,000 kilometers. If you just plug these numbers into those relations, that's the number you can get. It's different, a little bit different. This, what you can actually see in terms of the aftershocks is quite a bit longer. So this is a rough estimate. I mean, that's what it's intended to give a rough estimate. Yeah. Yeah, in every case, all of these magnitude scales have a correction factor for the distance from the fault. So we're accommodating that in all these cases. Yeah. Why are body wave magnitudes not good for large magnitude earthquakes? It's simply because once you get up to a certain point with the size of earthquakes, the body waves don't get any bigger. And the reason for that is that what you're actually measuring is the amplitude of the body wave, the P wave, we're measuring the P wave, so it's the amplitude of that first wiggle that arrives at your station. When we talked about these large magnitude earthquakes, remember that the rupture took more than 5 minutes to get from here to here. So at every point during this rupture, P waves are being generated from the fault, right? So once you get above a magnitude 6, of course there is more energy being radiated, but it takes more time for the energy to leave. And so that's why the P wave doesn't get any bigger, the P wave just goes on for longer. Okay, great question. Anybody else? Yeah. The moment magnitude, yeah, so the Richter magnitude is a separate scale, just like we have a body wave scale, a surface wave scale, a moment magnitude scale. A Richter magnitude is just another scale. It's most similar, actually it's not on here, to local magnitude. So all of these are intended to be similar to one another, but they're never identical to one another because they're all empirically defined and they're all defined differently. But the intent has always been that they're intended to be about approximate, although there are limitations, right? So body wave magnitude doesn't work above a magnitude 6 earthquake. Any other questions? Okay, so you should now start working on assignment number 3, which is looking at locating earthquakes and doing magnitudes for earthquakes. All right, thank you.